Hi, everyone. In the last lecture, we talked about electrons and specifically where those electrons are orbiting relative to the nucleus. We talked about electron shells and the fact that in this class, you only need to know about the first, second, and third electron shell. And remember that the first shell holds a maximum of 2 electrons, and you can see that helium has 2, so it has a full outer electron shell. Then the second shell, remember, holds a maximum of 8 electrons, and you can see that neon has 8. So that would be a full outer electron shell for neon. And then finally, that third shell also holds a maximum of 8. And you can see that argon has 8 in the outer electron shell. So it also has a full shell. Oops, sorry, I didn't mean to do that yet. If you look at hydrogen, lithium, sodium, they all have 1 electron in that outer electron shell. And that is because we can sketch the electron configuration and determine that, but we can also look at the periodic table, and the shortcut is looking at these Roman numerals over these 8 columns. So skipping the metals in the middle here, column 1 being this column with hydrogen, lithium, sodium, everything in column 1 has 1 valence electron, meaning 1 electron in that outer electron shell. Everything in column 2 has 2 valence electrons. So beryllium, magnesium, calcium, and so on have 2 electrons in that valence shell. Skipping over here to the column with boron and aluminum and gallium, everything in this column has 3 electrons in the outer electron shell. If you haven't had Roman numerals in a while, you could think of these just as a normal number. You could write a 1, 2, 3, 4, 5, 6, 7, 8 over these 8 columns. So column 4 with carbon, carbon has 4 valence electrons, nitrogen has 5, oxygen has 6, fluorine has 7, and finally neon has 8. Obviously, column 8, helium only has 2 electrons total, so it does not have 8 in the outer shell, but it does have a full valence shell. And everything in column 8, because it already has a full outer shell, it doesn't need to do anything to fill that shell, which means it is inert. Everything in this column is inert, meaning non-reactive, already stable. These atoms don't need to do anything to fill their outer electron shell. It's already full. The other 7 columns, though, are going to have to do something to fill that outer electron shell. And they're going to have a couple of options that we're going to talk about today. But this is your shortcut to finding out how many valence electrons an atom has, and we will come back to this in a few minutes. Okay, next I want to go to my iPad and write some statements for you and start drawing some ways that atoms can either share electrons or gain or lose electrons to complete that outer shell. So every atom must have a full valence shell to become stable. And one way that atoms can achieve that is through sharing electrons. When 2 atoms share electrons, they form what's called a covalent bond. This is the first of 3 types of chemical bond that we're going to talk about. Covalent bonds involve 2 atoms sharing electrons. And 2 or more atoms bonded together is what we call a molecule. So today we're going to be looking at molecules for the first time in this class. What do I mean by sharing electrons? Well, let's look at the periodic table again for a minute, and you'll recall that hydrogen is atomic number 1. Now today I am only interested in the number of electrons that each atom has, because we're only talking about electrons today, not protons and not neutrons. Atomic number 1 tells us that hydrogen has 1 electron. And remember that electron would be located in the first electron shell, which holds a maximum of 2 electrons. And hydrogen has 1. So hydrogen is not stable. It has 1 open spot that it needs to fill to become stable. Also remember, hydrogen is in column 1, which tells us that hydrogen has 1 valence electron. Okay, similarly, let's look at carbon. Carbon is atomic number 6, which means it has 6 electrons total. And it's in column 4. So column 4 tells us that carbon has 4 valence electrons. The other way we can know that carbon has 4 valence electrons is to sketch it. So carbon, I'm writing the chemical symbol of the element in the nucleus this time, so we can keep track of which atom we're talking about here. So first electron shell holds 2, and obviously carbon has more than 2, so those other electrons are going to go in the second electron shell, which holds a maximum of 8 electrons. And I'm going to draw carbon's green. So 1, 2, 3, 4, 5, 6. I've drawn them that way specifically so I can show sharing of electrons with carbon and hydrogen. So carbon has 4 valence electrons. That means that carbon has 4 spots that need to get filled for carbon to become stable. And one way that carbon can do this is to share electrons with another atom. In fact, it can share with that hydrogen. So let's see what that would look like. Here's our carbon again. 2 electrons in the first shell. And then 4 in the next shell. So that's atomic number 6, column 4, so 4 valence electrons. That means there are 4 spots out here that still need to get filled for carbon to become stable. And one way it can do that is to share electrons with hydrogen. If this hydrogen comes over and shares its electron with carbon in this spot, now that hydrogen has a full outer shell. And in that spot, carbon has a full outer shell. And what if 3 other hydrogens come along and do the same thing? So this hydrogen is going to share an electron with carbon, and carbon's going to share an electron with that hydrogen. The same thing here, and the same thing here. Again, I'm just writing the letter of the element, the chemical symbol in that nucleus, rather than drawing protons and neutrons, because today I'd rather keep track of what atom that is rather than tracking protons and neutrons that really don't matter in this story. So this hydrogen has an electron that it shares with carbon, and this one has an electron it shares with carbon. And now here's the story. Those electrons no longer belong to hydrogen or carbon. They belong to both. And they're orbiting so quickly that you couldn't freeze it and go, now they're with hydrogen, now they're with carbon. They're truly orbiting both. So these 2 electrons are orbiting around hydrogen and around carbon. And same for all of them. They are now shared. So now carbon has a full outer electron shell and hydrogen has a full outer electron shell. That sharing of electrons, each place that is happening is called a covalent bond. This, oops, didn't mean to do that, sorry. God, sorry about that. This is a covalent bond. sharing one pair of electrons in that spot. This is a covalent bond, this is a covalent bond, this is a covalent bond. In this case, we would call that a single covalent bond because those atoms are sharing one pair of electrons. We're going to look at double and triple bonds today also. Triple is as many pairs as you can share. A double bond is going to be sharing 2 pairs of electrons. A triple is going to be sharing 3 pairs of electrons, but you'll see that in a minute. A simpler version that you'll more commonly see showing that sharing of a pair of electrons is every place there's a sharing a pair of electrons, you just draw a straight line. So a simpler version of this molecule, this is a molecule because it's 2 or more atoms bonded together. They're sharing electrons to become stable. Each one of these lines means sharing 1 pair of electrons. So that is a covalent bond. That is a simpler version of that molecule. The chemical formula for this molecule would be CH4. Subscript 4, that tells us it's 1 carbon and 4 hydrogens, and they're bonded together. This is a molecule. In fact, this molecule is called methane. It is the simplest organic molecule. Organic molecule meaning carbon is in that molecule. Single covalent bond sharing electrons. These bonds, covalent bonds, are very strong. They are difficult to break. And in fact, they require energy input to form. That energy gets stored in the covalent bond. So that energy input is now stored in the covalent bonds. And when those bonds are broken, specifically the covalent bonds is what we're talking about, energy is released. This is hugely important in biology because the way you get energy from your food molecules is breaking the covalent bonds of those food molecules. The most important molecule that you eat is glucose. Glucose has a chemical formula of C6H12O6. That means that it's a molecule with 6 carbons, 12 hydrogens, and 6 oxygens all bonded together, and they are covalently bonded together. When you break the covalent bonds of that glucose molecule, that energy is released, and we repackage that as a molecule that's going to be the energy currency of the cell called ATP. So in the cell, we break the covalent bonds of glucose to form ATP. And that ATP is the energy currency of the cell. What that means is we need the energy from glucose to drive chemical reactions in the cell, but we can't directly use glucose to do that. We have to convert it to something that the cell can use, and that's ATP. Kind of like when you travel and you're in a foreign country and you need to buy something, you need to exchange your US dollars for a different type of currency in order to be able to buy something. In the cell, we have to exchange glucose to a version of energy that the cell can accept and use, and that is ATP. That energy comes from the covalent bonds of glucose. Let's just quickly look at glucose in linear version. You'll see this again in a future lecture when we talk about carbohydrates, and you'll see it again when we talk about how we make ATP from glucose in a process called cellular respiration. You'll learn about cellular respiration in detail in this class. 6 carbons, every one of those lines is a single covalent bond, which means sharing 1 pair of electrons. Sorry, I messed up there. That flip right there is purposeful. You're about to see our first double covalent bond. Okay, a couple of things about this that are really important. Number one, every time there's a line, that is a covalent bond, sharing electrons to complete the outer electron shells of those atoms. This is a double covalent bond. Which is sharing 2 pairs of electrons. To understand why 2 pairs of electrons are being shared in that spot, oxygen is in column 6. It's atomic number 8. It has 6 valence electrons. It has 6, it needs 8 to complete that outer shell. That means it needs 2 more electrons to complete its outer shell. One way it can do that is to share 2 pairs of electrons with another atom. Now, oxygen has a full outer shell. Carbon needs to share 4 pairs of electrons. Remember, carbon has 4 in the outer shell. That means carbon needs to share 1, 2, 3, 4 pairs of electrons to complete its outer shell. Looking at this carbon on the end, that carbon is sharing 1, 2, 3, 4 pairs of electrons. So again, this double bond counts as sharing 2 pairs of electrons. Let's look at the next carbon over. 1, 2, 3, 4. This one. 1, 2, 3, 4. The next one over. 1, 2, 3, 4. Sorry, that was supposed to be right on top of that one. Next one over. 1, 2, 3, 4. And then one more. 1, 2, 3, 4. So every one of those carbons is sharing 4 pairs of electrons to complete its outer shell. That is now a very stable molecule. Those bonds all contain energy. And when those bonds are broken, that energy is released and it can be converted to a currency that the cell can use to power chemical reactions in the cell. Combusting glucose to release that energy contained in the covalent bonds and convert it to ATP through a process called cellular respiration is the most important chemical reaction that happens in your body. In fact, you make and use your body weight in ATP every day. The second you stop making ATP, you die. You have to have a constant supply of ATP in the body. It powers every chemical reaction in the cell that requires energy. And that's a lot of different things. So covalent bonds are really important to understand in biology. They're the strongest chemical bonds. They require energy input to form. When they're broken, that energy is released. And that is how some atoms can complete their outer electron shell and become stable, is by sharing electrons to complete that outer shell. So a double bond is sharing 2 pairs of electrons, and a triple bond is 3 pairs of electrons. So let's write all 3 kinds of covalent bonds here. Single covalent bond, sharing 1 pair of electrons. And a good example of that was methane. Double covalent bond is sharing 2 pairs of electrons. And you saw that double bond in the glucose molecule, but oxygen is also double bonded to oxygen to form O2. And lastly, a triple covalent bond is sharing 3 pairs of electrons. And that's the most 2 atoms can share. Remember that these bonds require energy input to form. The double bond requires more energy than a single. So a triple is going to require a lot of energy input. And there's not enough energy available to form a quadruple bond. Nitrogen is triple bonded to nitrogen. That would be N2. That's what you need to know about the difference between single, double, and triple bonds. You don't need to know any more than that. There is another part of the story, though, that's important to realize, and that is when 2 electrons, when 2 electrons are shared, so when 2 atoms are sharing 1 pair of electrons, they're not always shared equally. That becomes a little bit confusing. But in the next video, we're going to talk about hydrogen bonds. And in hydrogen bonds, there's covalent bonding that happens between atoms. And that's going to set the stage for something else if those electrons are not shared equally. So we're going to have equal sharing of electrons. Which is going to result in what's called a non-polar covalent bond. And then the other option is unequal sharing of electrons, which is going to result in what's called a polar covalent bond. And I will explain that in the next video.